In this visualization, a digital lock shatters from the inside out. This demonstrates the impact of capturing a victim's password reset token entirely remotely, bypassing their security without ever touching their actual computer. Today, we are demonstrating how to execute a host header injection attack to achieve full account takeover. Host header injection is a vulnerability where an attacker manipulates the HTTP header that specifies which website domain the user is trying to access. Successfully identifying this flaw often leads to significant bug bounties. To replicate this in a lab, we need an intercept proxy, a custom listener server to monitor incoming traffic, and a target web application with a forgot password feature. An intercept proxy is a tool that captures web traffic between your browser and the server, allowing you to modify requests in real time. This attack weaponizes the password recovery process. Instead of attacking the server's perimeter, we use the application's own logic to deliver sensitive credentials directly to a server we control. We begin by triggering a standard password reset for the victim's email address on the target website. We catch the resulting post request using our proxy before it leaves the browser. An endpoint is the specific web address where an application receives and processes requests. Here, the request is paused as it attempts to reach the password reset service. Within this request, we look for the host header. The host header is a mandatory field in an HTTP request that tells the server which domain the user is trying to visit. In our first attempt, we simply append the URL of our custom listener server to the end of the existing domain string in the host header. We forward the modified request. The data block flows into the server, and a green 200 OK status indicator returns. The 200 OK response confirms the server accepted the formatting of our request. To determine if the injection worked, we must see how the backend processed our modified host header. We now check the victim's email inbox to inspect the reset link generated by the server. The hyperlink in the email is mangled and unclickable. It appears the server's security filters attempted to sanitize our input. The server's defensive logic recognized an anomaly. It allowed the request but stripped the .com extension from our injected host header. This diagram shows the text passing through a filter. When the filter deletes the .com, the remaining text blocks slam together. This concatenation destroys the URL structure, preventing the link from functioning. Standard payload injection failed because of this input sanitization. Bypassing it requires us to find an edge case in how the server parses the host header. We return to our intercepted post request to try a different syntax. This time, we insert a colon between the target domain and our listener URL. This exploits a parsing loophole. Web servers interpret text following a colon as a port number. When the server's logic hits the colon, it diverts our listener URL into a bucket for port data, separating it from the core domain. The server ignores this assumed port data during its security checks, but it still reflects the entire string into the outbound email template. This bypasses the sanitization filter that blocked our previous attempt. Identifying specific syntax behaviors, like how a server handles port designations, is what turns a filtered request into a successful exploit. We check the victim's inbox again. This time, the reset link is perfectly formed and points to our malicious listener. The victim clicks the link, unaware the destination has been altered. In this visualization, a packet of light launches from the legitimate site into our listener server in the shadowy void. We switch back to our custom listener interface to check for incoming traffic. We have a hit. The listener has captured an HTTP GET request from the victim's browser. A GET request is a standard web method used to request data from a server. Within the captured GET request URI shown here, we can see the result of the injection. A URI, or Uniform Resource Identifier, is the string used to identify a resource on a network. The victim's secret reset token is now visible in our logs. This isolated temporary token is the definitive proof of the exploit. We can now use this value to navigate to the reset page and finalize the account takeover. To complete the attack, we use the stolen token to access the legitimate reset page and change the password. The victim is now locked out of their own account. This occurred because of a dynamic host architecture. The server trusted the host header provided by the user to build its outbound links, rather than using its own internal configuration. To prevent this, developers should always use hard-coded server configurations and environment variables to generate internal links. User-supplied headers must never be trusted for routing or URL generation. Understanding how servers parse protocol syntax allows researchers to find flaws that basic security filters miss. Mastering these logical edge cases is essential for finding high-value vulnerabilities. Continue practicing these techniques in your own secure lab.